Let's do a problem. A turntable set for 45 RPM is turned on and reaches its operating speed in 1.25 seconds. What is the average angular acceleration of the turntable? Well, I'm sure some of you at least know what a turntable is. A disc that rotates. When you turn it on, the moment you turn it on, its initial angular velocity is 0. It picks up angular velocity and it reaches the operating speed. What is the operating speed? Is 45 RPM. So we have initial angular velocity omega 0 equal to 0. The final angular velocity, you can see 45 RPM is actually the angular velocity, revolutions per second. You need to convert it to radian per second. How do you convert revolutions per minute? Not revolutions per second. This is revolutions per minute. How do you convert that to radian per second? You see, each revolution is 2 pi radians. So 45 revolutions is 45 times 2 pi radians. That will be 45 times 2 pi radians per minute, which is 45 times 2 pi radians divided by 60 radians per second. So 45 RPM is 45 times 2 pi divided by 60 radian per second. In other words, 45 revolutions is 45 times 2 pi radians, and so many radians are described in 1 minute, which is 60 seconds. Therefore, 45 RPM is the same as 45 times 2 pi divided by 60 radian per second. To convert revolutions per minute to radian per second, multiply by 2 pi divided by 60, and that is 4.7 radian per second. So the turntable changes its angular velocity from 0 to 4.7 radian per second in this time of 1.2 seconds. Therefore, alpha equal to omega f minus omega 0 divided by t. That will be 4.7 minus 0 divided by 1.25 seconds. That is 3.8 radian per second squared is the angular acceleration. Alright, let's now look at equations of rotational motion. Well, you know your equations of linear motion, don't you? What are the equations of linear motion? We've got Vf equal to V0 plus At, one equation. What's the second equation? X equal to X0 plus V0t plus 1/2 At squared. The second equation. The third equation is Vf squared equal to V0 squared plus V0 squared plus 2ax. You can actually translate those equations for linear motion to describe rotational motion by replacing linear velocity by angular velocity, linear acceleration by angular acceleration, and linear displacement by angular displacement. Now, you can see here, the linear velocity is v. So let me say linear and rotational. Linear velocity is v, rotational velocity is omega. Linear acceleration is a, rotational acceleration is alpha. linear displacement we generally call x or y and so on. The rotational displacement is theta. So what all you need to do is write down the equations for linear motion and replace your v by omega, a by alpha, x by theta. You have your equations for rotational motion. Let's do that. Now, we can write corresponding equations for rotational motion by replacing v by omega, a by alpha, and x by theta. Alright, let's write those equations. Linear equations. We've got v equal to v0 plus at. In place of vf, I simply wrote v, velocity at any given time. Tell me, what is the corresponding rotational equation? Well, simple. Replace v by omega, a by alpha. We get omega equal to omega 0 plus alpha t. Alright, the second rotational equation, x equal to x0 plus v0t plus 1/2 at squared. X will be replaced by theta, v0 by omega 0, and a by alpha. We got theta equal to theta 0 plus omega 0t plus 1/2 alpha t squared is the second rotational equation. What is the third linear equation? V squared equal to v0 squared plus 2ax. And in rotation, it becomes omega squared equal to omega 0 squared plus 2 alpha theta. You can see I have used here omega for omega f, v for vf. Okay, we can now use these rotational equations to solve problems. Let's do a small problem. A 33.3 RPM record on a turntable uniformly reaches its operating speed in 2.45 seconds once the record player is turned on. What is the angular displacement during this time? What is the number of revolutions of the disk during this time? What is the corresponding arc length on the circumference of the 15 centimeter diameter record? Alright, first of all, we need to find the angular displacement. Well, that means we need to find the angular acceleration. So, let's pick our data. Initial angular velocity omega I equal to 0. T is 2.45 seconds. The radius of the disk is 0.075 second. Is that right? Yes. 15 centimeter is the diameter. That means its radius is 7.5 centimeter, which is 0.075 meter. Well, what is the final omega? It reaches the operating speed. What is the operating speed? 33.3 RPM. This is the final angular velocity. Initial angular velocity is 0. In 2.45 seconds, it reaches the operating speed of 33.3 revolutions per minute. Convert revolutions per minute to radians per second. Multiply by 2 pi and divide by 60. So that will be 3.5 radian per second. Now you can use these values to find alpha. Alpha equal to omega f minus omega 0 divided by t. That will be 3.5 minus 0 divided by 2.45 seconds. That is 1.43 radian per second squared is the angular acceleration. Well, we know the angular acceleration, we know the initial angular velocity, we know the time. Can you calculate the angular displacement during that time? What is the equation we will use? Well, this is the equation for angular displacement. Theta equal to theta 0 plus omega 0 t plus 1/2 alpha t squared. Theta 0 is 0, omega 0 is 0, therefore theta equal to 1/2, alpha is 1.43, t is 2.45 seconds. So that will be 4.29 radian. The angular displacement is 4.29 radian. What is it that we want next? What is the number of revolutions of the record during this time? How many times did the record go round during this time? Well, you know that if the record goes round once, the angular displacement will be 2 pi radians. That means there are 2 pi radians in one revolution. And you know that the disk rotated through 4.29 radians during that time. Now, this 4.29 radians correspond to how many revolutions? One revolution corresponds to 2 pi radians. Therefore, 4.29 radian will correspond to 4.29 divided by 2 pi, number of revolutions. So, the number of revolutions is the angular displacement divided by 2 pi. I hope you understand that, because each revolution is 2 pi radians. Therefore, an angular displacement of theta will correspond to theta divided by 2 pi revolutions. That will be 4.29 radian divided by 2 pi radian, which is 0.68. So the disk went through not completely one revolution. It completed 0.68 of a revolution. How about the last part? What is the corresponding arc length on the circumference of a 15 centimeter diameter record? Well, what is the relation between arc length and the angular displacement? Well, what happened here is the disk went through, described an angular displacement of how much? We got theta equal to 4.29 and the radius is 0.075 meter. You see, the disk rotated through an angle of 4.29 radians, and therefore the linear displacement, the displacement along the arc, the corresponding arc length equal to a radius times the angle, arc length equal to r theta. Alright, so that gives us, if delta s is the arc length, then delta s equal to r times theta. R is 0.075 meter, theta is 4.29 radian, therefore the length of the arc for that revolution is